This is the document we were discussing last time. We went through a lot of numerical examples. I'm quickly rushing through them once again. Parallel connection was there, series connection was also there, and compound connection was also there. Okay, one piece of advice, that's why I'm going through it once again, is that when it comes to including voltage drop due to the brushes, like in this problem, we were given 1 volt drop due to each brush. Okay, so the calculation that we did was fine. It was a parallel connection. We did all the calculations. Then in the next problem, we were asked to calculate the voltage regulation. Here we have not mentioned one assumption which has been made, that the no load voltage will be the same as back EMF, which can be a okay assumption, nothing wrong with it. But if at no load the generator is still running at full speed, then 2 volt drop may still be there. Then no load voltage actually will be EB minus 2 volt. And if at no load we have decided to reduce the speed of the generator significantly, then this 2 volt may disappear. 2 volt appears only because of the friction between the brushes and the rotating parts. So if the generator is running at full speed even at no load, then the no load voltage actually will be EB minus 2 volt. But I'm ignoring that 2 volt effect in voltage regulation calculations. I thought I'll point this out to you. Okay. Same thing applies to this problem also, where we have got a series connection. Again, when it comes to voltage regulation calculations, I am ignoring brush drop completely. That was one thing I wanted to point out. We went further in this document. We saw several problems. I think you can go through them once again for your own safety. We saw 2 cases of compound winding. One was called long shunt because the shunt part of the field winding was away from the armature, and the other was the short shunt where the shunt part was close to the armature and the series part was slightly away when it was the second element rather than being the first element. These calculations are simple once you know what we mean by short shunt and long shunt connections. So these calculations are there. We did them last time as well. Now, some more problems in this document. I'll quickly rush through them and then we will start talking about DC motors. This problem is a straightforward example of the well-known equation for EB. A 4-pole wave wound means capital A equal to 2. DC generator has 51 armature slots and each slot contains 20 conductors. So Z is 51 multiplied by 20. What will be the voltage generated in the machine when driven by a wind turbine at 150 RPM? Okay. Assuming that the useful flux per pole is 70 milliweber, 70. So I have taken phi as 70 multiplied by 10 raised to the power minus 3, Z as 51 into 20, capital N is 150, number of poles is 4, divided by 60 into 2, because wave wound construction has capital A equal to 2. So the result is 357. Simple question, simple answer. Next one, an 8-pole DC generator has 500 armature conductors and a usual flux of 0.05 Weber per pole. What will be the EMF generated if the generator is lap connected and runs at 1200 RPM? That's one part. What must be the generator? What must the generator speed be if it produces the same EMF but is wave bound? So I think you can do it yourself. It's very straightforward. I have given you the answers. Try to do it yourself. It should be easy enough. Okay. The next one is about a separately excited generator. It is running at 1000 RPM. When it supplied 200 amperes at 125 volt, then it was running at 1000 RPM. That is the initial condition given. What will be the load current when the speed drops to 800 RPM and field current is unchanged? Remember, here IF is totally independent. It doesn't change with load. Even in parallel connection, it is the same story, but in series connection, it is not, for sure. Armature resistance is given as 0.04 ohm. Total brush drop is 2 volt. That's also given. Field resistance is not given. But they are telling you that field current remains unchanged. Okay, so what do we do? If the speed drops, you know that EB is phi ZNP divided by 60A. So EB is directly proportional to N, assuming that phi is constant. For a separately excited case, as long as IF is constant, you can assume phi to be constant. So let's see what we do. But you don't need that actually. What you need is, in the first part at least, straightforward application of KVL. Terminal voltage is given as 125 volt. So put that there. Because it's a separately excited case, the load current is same as armature current. So armature current is 200 amperes. Armature resistance is given as 0.04 ohm, and plus you include 2 volts because of the brushes. So EB turns out to be 135 volt. That's first part. Now in the second part, when N drops by a factor of 0.8, it has become 800 RPM, while previously it was 1000 RPM, right? So I'm just double checking. Yeah, 1000 RPM to 800 RPM. So the change is by a factor of 0.8. So EB would also drop by the same number because phi is constant and everything else is constant in the equation anyway. So 135 multiplied by 0.8 will give you the new EB, which is 108 volt. Now, to calculate the new current, you need to do a bit of extra calculation here, which we normally don't do. First, calculate the load resistance based on case A, where we knew the current and the voltage. 125 volt was the output voltage, the terminal voltage, and 200 amperes was the current. It's a DC machine, so purely resistive load will be applied. So the load resistance, according to the data given in case 1, is 0.625 ohm. In case 2, terminal voltage will now be given by the new back EMF minus 2 volt minus IARA. And terminal voltage is also IA into RL. So compare the two and you get IA. Bit of trick here. And once you get IA, V is easy to figure out using V equal to IA into RL. Or equation 1, whichever way you want to do it. So this problem requires a bit of extra calculation which we normally don't do, that is calculating the load resistance. Some more problems. A 4-pole DC generator has a wave-bound armature with 792 conductors. The flux per pole is 0.0121 Weber. Determine the speed at which the generator should run to generate 240 volt at no load. Straightforward application of this equation. Do the calculations, you should get this number, 751.3 RPM. Hopefully there is no mistake in my calculations. Okay. Next one is slightly more interesting. A DC generator, when driven at 1000 RPM, something has been missed in scanning, but it's clear, I think, that 1000 RPM is meant here. With a flux per pole of 0.02 Weber, produces an EMF. F has been missed here. Produces an EMF of 200 volt. If the speed is increased to 1100 volt, 1100 RPM, and the flux per pole is reduced to 0.019 Weber per pole. Again, per pole has been missed here, but you can easily guess what has been missed. What will be the new value of EMF? So in case 1, let's go systematically about it. In case 1, you are given EB as 200 volt, phi is given as 0.02 Weber per pole of force. Z is an unknown, N is given as 1000 RPM, E is an unknown, 60A is an unknown. So using the data here, you can figure out the value of ZP upon 60A for this machine. You don't need to know Z, P, and A separately. What you need is this entire factor, ZP divided by 60. That can be figured out based on data given in case 1. It turns out to be 10. Now in case 2, you use that factor directly and use the new value of phi and N. New phi is 0.019 Weber per pole and new N is 1100. Put those values and use the formula for EB with the assumption that ZP divided by 60A is unchanged, because the machine is the same anyway. Okay. So the answer is 209 volts. Third one is also, I think, straightforward. I have not probably drawn the diagram here, but it's a very straightforward calculation. Shunt DC generator. You can go through it yourself. It's very similar to what we have done previously in several problems. And I think this is the last one. Calculate the flux per pole required on full load for a 50 kilowatt, 400 volt, 8 pole, 600 RPM DC generator with 256 conductors arranged in a lap connected winding. You have to read the problem carefully. A lot of data is given here. The armature winding resistance is 0.1 ohm and the shunt field resistance is 200 ohm. And there is a brush contact voltage drop of 1 volt per brush. Okay, we will assume shunt connection, although it's not mentioned, I think, anywhere, but they have given you shunt field resistance. So that means they mean shunt connection between armature and field windings. So for that connection, you know the diagram by now. What we do is first calculate the load current, which is 50 kilowatt divided by 400 volts. That gives you 125 amperes. Field current is terminal voltage divided by field resistance. So 400 divided by 200, it comes out to be 2 amperes. The difference between I and IF, sorry, this okay, no, this cannot be right. Total load, no, this is a mistake. Sorry. What I think I'll have to correct this part also. This total armature current will be summation of 125 and 2 amperes. Right? It's a generator. Okay. Yeah, it's a generator. So this number is wrong. I'll have to correct. I'm sorry about it. Let me correct this number quickly. But use 127, not 123, and calculate EB. That's the way to go. And once you have got EB, you use the well-known equation EB equal to phi ZNP divided by 60A to calculate what they want you to calculate. Flux per pole required. Everything else is given. You plug it in. So the value of phi can be calculated. Don't believe the numbers. They'll have to change a little bit. I'll change that and send you the document once again. Yeah. I don't know how I made that stupid mistake. I was assuming motor for some reasons. Anyway, the last one is here. 4-pole wave-wound generator has 51 slots, each with 20 conductors. I think we have done something like this in the past. Calculate the EMF if the speed is 1500 RPM and the flux per pole is 7 milliweber. Yeah, this is something that we have done, I think, already. 350, yeah, this problem has been done in the past. It's just that it's taken from a different document. Last one is also pretty easy. It's a shunt generator. It has no load terminal voltage, which is EB. It is 127 volt. Calculate the load current if the terminal voltage is 120 volt. Yeah, it should be very easy. EB is given, V is given. IA is EB minus V divided by RA. Straightforward, 350 amperes. And this is also taken from some other source. This is a straightforward calculation example again, using the equation EB equal to phi ZNP by 60. In this case, they are calling it E rather than EB, not a big issue. You can tackle it by yourself, okay? So I'll make one correction in this document and we'll send you this document once. Some numbers in that particular problem need to be updated. So that is as far as the generators, DC generators go. Now let's talk about DC motors. They are more popular than DC generators. As far as the construction is concerned, there's hardly any change between a DC generator and a DC motor. Same thing, a rotating armature and a stationary stator. Stator and rotor are the correct words. Stator has all the magnetic poles. Rotor has the rotating conductors on them. The electrical portion of the rotor is known as armature. But here there is no mechanical input. In fact, the output is mechanical. The output is a rotary mechanical power. Input is a DC electrical power. Okay. Now again, a DC motor can be either separately wound or shunt wound or series wound or compound wound. Let's look at each of the cases carefully and the equations that we would need. Now, one thing which is different in a motor compared to the generator is the terminal voltage is higher and back EMF is lower. Now you are supplying the terminal voltage. In generators, you are actually getting terminal voltage. Now you are supplying the terminal voltage for a motor. So VT will be higher compared to EB. In a separately excited case, obviously, the field winding is independently fed using a separate DC source. And the second DC source, of course, is feeding the armature to generate the rotation. I've repeated a bit of what we have done already, just for the sake of completeness. VT denotes terminal voltage, that is voltage applied to the motor. RA is the resistance of the armature winding. RF is the resistance of the field winding. IF is the field current. IA is the armature current. The terminal current IT. Now, by the way, I'm using the suffix capital T. In generators, I was not using any suffices for output voltage and output current. But here I'm deliberately using IT and VT for terminal voltage and terminal current. So the terminal current IT in this particular case, that means in the case of a separately excited motor, will be simply the same as armature current, because field current is totally independent. That's equation 1. Back EMF equation is same in a motor as it was in the generator. Phi Z and P divided by 60A. Okay. For wave-wound DC motor, number of parallel paths is P. For left-wound case, it is, for wave-wound it is 2, and for left-wound it is P, as it was in the case of DC generator. Well-known things. Now it's a separately excited case, so IF is VF divided by RF. Straightforward. Okay, and IA or IT can be written as VT minus EB by RA. As I told you, VT is higher compared to EB in this case. So 3 equations are IT equal to IA, IF equal to VF divided by RF, and IT equal to IA equal to VT minus EB divided by RF. Mechanical power that you are getting from this motor is normally written as PM. Small m denotes motor. It is connected to the torque by equation 7. Tm is the motor torque, which is measured in Newton meter. Torque is basically action at a distance. You know this definition, I'm sure. Omega is the angular frequency, which is 2 pi capital N divided by 60, as we have seen in the past. Yeah, it's right here. If you talk about RPS rather than RPM, then you use the symbol small n, which is capital N divided by 60. In some numerical problems, they give you RPS rather than RPM. So be careful when reading the problem. Omega is 2 pi multiplied by small n, because small n is capital N divided by 60. Now, another term that is coined in case of DC motors is electrical power rather than the mechanical power. Electrical power is defined as back EMF multiplied by armature current. This is the power, electrical power produced by the armature, from where mechanical losses will be subtracted to get the mechanical power. EBIA is the electrical power output minus mechanical losses, which is P loss M, will give you the mechanical power output, PM. Okay. If mechanical losses are negligible, then EBIA will be simply as the mechanical power output. Now, electrical losses, as we saw in case of DC generators, will have two parts. One will be the copper loss, the other will be core loss. Let's say that electrical loss total is P loss E, and mechanical loss total, which includes windage and friction, it's P loss M. Then input power, which is VT into IT, by the way. Input power is straightforward if you look at the diagram. It is VT into IT. Okay. So input power minus the two loss powers will give you the mechanical output power. This is the power equation. This actually will apply to AC machines also, but right now let's concentrate on DC motors. Input electrical power minus electrical power loss minus mechanical power loss equal to output mechanical power. Common sense. Now, electrical losses will have copper losses, which are IA square RA plus, okay. In this case, I have excluded IF square RF because it's a separately excited case. IF is not, even if there is loss in the field windings, it is not affecting the performance of the motor. So I've excluded IF square RF from the copper losses. It's my call. Maybe other people will disagree with this approach. Okay. And on top of it, we'll have hysteresis loss and eddy current loss, for which we know equations based on our discussions in case of transformers. But generally, these values are given to you based on experimental measurements. You don't need to remember those equations. Okay. I repeated this equation once again. Power balance. If mechanical losses are small, which is true for machines rotating at a lower speed, like, if you are, in case of generators at least, if you are using a wind turbine, then it would produce speeds which are lower, 150 RPM or so. But anyway, if somehow we assume that mechanical loss is negligible, then an interesting equation shows up. PM is approximately equal to PE, that means electrical output power, which is EBIA, equal to mechanical output power, which is omega TM, where time is generated. So if I equate these two and use the formula for EB, which is pi ZNP divided by 60A, I get what you see here. Omega Tm approximately equal to phi ZNP IA divided by 60A. For a given motor, Z, P and A will be constant. And it's a separately excited motor. Sorry, yeah, it's a separately excited motor. Yeah, we are looking at that. So phi would also be constant unless we change IF by changing EF, etc. But we ignore that possibility. Let's assume that phi is also constant. Then what happens? I'm trying to figure out the behavior of torque. Torque formula, if you simplify the result, turns out to be equation 20. Phi ZP IA divided by 2 pi A. And out of that, Z, P, and A are definitely fixed for a given motor. So torque is proportional to phi into Ia. And if phi is constant, then torque is simply proportional to armature current for a separately excited DC motor. The higher the armature current, the larger the torque generated. In fact, capital N has cancelled out. You see that interesting phenomenon. RPM doesn't matter in calculating torque. Okay. For a separately excited motor, phi, Z, P, and A are fixed. Hence, yeah, that's what I said. Torque is proportional to Ia. If by chance you make phi a variable by making the field supply variable voltage, then you can say that torque is proportional to the multiplication of phi and Ia. Now, phi is almost a linear function of IF for most practical situations, as long as IF is not too large. Because if IF is too large, then the magnetic material, or rather the windings, will saturate. You will not get any more flux. But ignoring that possibility, you can say that phi is proportional to IF. So torque, in another sense, is proportional to the product of IF and IA. Now for shunt excited case, this is the diagram. Now IT would be IF plus IA. For generators, it was different, Their IA was IT plus IF. For motors, it is slightly different because the current IT is coming in and then it is being broken into two components, IF and IA. IT would be the largest current here compared to the other two. For generators, it was the other way around. IA was the largest one and it was being broken into IF and IT. I was calling it I there. And of course, the second equation is again Vt minus IARA equal to EB, that's KVL. And third equation is IF equal to Vt upon RF. You can see the reason why these three equations are being written based on the equivalent circuit. IF is constant as long as you maintain the terminal voltage the same value, IF would be constant. So phi would be constant in this case. Okay. And if phi is constant, the situation is more or less similar to what we saw in case of a separately excited motor. Tm, you can work it out. I have not written because this case is very similar to separately excited motor. Tm will be proportional to multiplication of IF into IA. That means it will be proportional to multiplication of phi into IA, and phi is constant. So Tm in this case is also proportional to Ia as it was for separately excited motor. Now series excited motor is a very different case. Armature winding and field winding are in series. So IT and IA and IF are all the same. And the formula for them is Vt minus EB divided by Ra plus Rf. That's simple circuit theory. Now IF equal to Ia and Tm is supposed to be proportional to phi into Ia. and phi is proportional to IF, and IF is IA. So Tm is actually proportional to IA square, which is very different from separately excited motor or shunt excited motor. Here torque is proportional to square of the armature current. That is why even at lower armature currents, you get significant torque. And that is the main reason why DC series motors are used in applications where large starting torques are needed. Railway locomotives are one example. They need a lot of torque to get the train going. E-rickshaws also need large torque to get started. They all use DC series motors. Cranes also, elevators also in some cases use DC series motors because of this reason. Okay. Compound wound case obviously will have a mixture of what we saw in case of shunt wound motor and in case of series wound. I have written the equations, but based on what is given to us, we can do the calculations using elementary circuit theory. Part of the winding having resistance RF2, part of the field winding having resistance RF2 is in parallel with the armature, and the remaining part RF1 is in series. That is the basic idea. After that, calculations are easy to figure out. In this case, the behavior of the torque will be neither equation 29 nor equation 27. It would be somewhere in between. Torque will be neither linearly dependent on Ia nor it would be depending on Ia square. But something in between will be seen because you have got partially a shunt wound case and partially a series wound case. Depending on RF1 and RF2 ratio, you will know you are close to which case. If RF1 is very large compared to RF2, you are close to series wound case. If RF2 is very large compared to RF1, you are close to shunt wound case. Okay. So I don't want to predict anything in this case. It all depends. Compound wound case gives you an additional flexibility of optimizing or rather changing the performance of the motor to what is needed. The equation for dependence of torque on IA can be based on how much RF1 and how much RF2 you are using. Detailed analysis can be done if necessary. But important thing is that this method gives you an additional flexibility in terms of tailoring the performance of the motor. Okay. Now, one last thing. Today, I don't think we'll do any numerical examples on DC motors. But quickly, let me tell you that motor has a serious problem in starting. EB is phi ZNP divided by 60A, right? In the beginning, motor is not rotating. N is 0. So EB is 0. And assuming shunt wound case, in other cases also similar things will happen. But let's say it's a shunt wound motor. EB is 0 to begin with. If you apply full VT, and EB is 0, look at equation 25. RA is very small. It's 0.05 ohm or something. The value of IA that would occur if you apply full VT will be very large. Motor would burn, or at least it would get damaged. You cannot supply full voltage to the motor in the beginning. The resulting armature current will be too large. So what we do is we initially put a rheostat or a large series resistance in the armature path and get the motor going. As motor starts picking speed, we'll start reducing the value of that resistance and bring it to a small value when the motor has picked up the full speed and EB has become significantly large. This is called starter. This is what I've written here. When Vt is applied, motor is initially at a standstill, that is n equal to 0, which means EB equal to 0 in the beginning. Hence, a large armature current would flow and would damage the motor. Hence, we typically put a variable resistance or external in the circuit as shown below. Initially, our external is kept high, and as rotor starts picking speed and EB thereby starts building, we gradually reduce the external resistance value. I've done this with my own hands in the lab. It's a very effective method of making sure that motor starts smoothly without any damage being done to it. There's a large variety of starters. I would like you to do some self-study on this. I'll also give you some material later, but at least remember that the basic theory is not changing. It is just that how much variation. Generally, instead of having a continuous variation in our external, we have steps. One value of resistance, then second value of resistance, then third value of resistance, etc. So based on that, different practical implementations of the idea have been done, and they are given by different. They are given different names: 3-point starter, 4-point starter, etc. Thyristor starter is another story. A semiconductor device is used here. If time permits, I'll come back to this topic. But in the meantime, feel free to do some literature search on these things. A lot of starters are available in the market for DC motors. And depending on the application and depending on the motor nature, whether it's very large motor or very small motor, you may choose a particular starter. The simplest one, of course, is a single variable resistance in series. That's it. Okay. So I think I'll stop here today. Next time we will first do numerical examples, and then we will move on to two very important topics related to DC motors. One of them being how to control the speed of a DC motor. There are several methods. And the other one is the performance characteristics of the DC motor, things that matter to the customer. Okay. I think for today, this